All right, there we go. That's better. Okay, so thank you everyone for coming. Very much appreciate it and happy to see you here. We have a wonderful event. My name is Eric Wall. I am the chair of the local section of AIAA, which is, for those of you who don't know, is the American Institute of Aeronautics and Astronautics. And we are basically the largest professional organization for people in the aerospace field. And we do many different things, and happy to talk more about that, so please come and find me afterwards. But one of the things that we do is put on events like this and other types of events throughout the year as well. And anyway, without much further ado, we'll jump into tonight's event. Like I said, come and find me afterwards if you want to talk about anything else. So I'd like to welcome our speakers. Mr. Ken Bauer is a Silicon Valley research engineer with a curious educational path which has led him to support physics and astrophysics projects at NASA and Stanford University. He built and integrated systems of the Gravity B probe before joining SOFIA to coat its primary mirror and then plan many of its missions, occasionally serving as the last-ditch backup mission director. He enjoys presenting scientific topics to non-technical audiences of all ages and backgrounds.
So be prepared for non-technical.
Dr. Randolf Klein received his PhD in astrophysics from Friedrich Schiller University. Did I say that right? In Jena, Germany. As a postdoctoral researcher, he joined a team in Germany developing a far-infrared spectrometer for SOFIA. The decade-long development effort brought him via UC Berkeley to the SOFIA Science Center at NASA Ames, where Dr. Klein worked in various roles in science operations and outreach for SOFIA. That included frequently flying with SOFIA, executing its observation program. So please help me welcome our guests.
Good evening. I'll go first, and I'm going to tell you what SOFIA is and why we need it. And Randolph will tell you what it's done. And as I said, I often present to non-technical audiences, so those of you that are expecting it to be high-tech, please appreciate me now. SOFIA is an observatory, and it's an acronym, SOFIA. That's a big mess of words. Most of you probably know what astronomy is, the study of everything beyond the Earth's atmosphere. And I trust that everybody knows the preposition for. But the other words, stratospheric observatory and infrared, can be a mouthful for some people. So I'm going to start by explaining what those are. So there's a lot of kinds of light in the world. Usually when we think about light, we think about the things that our eyes see. And light comes in many, many colors. But it turns out it comes in a lot of colors, spectrums, wavelengths, that we cannot see. So here the sun has very conveniently provided some light, which has been divided by a prism or by a few trillion raindrops there in order to show us the spectrum of visible light. But that's only a small fraction of it. A little bit of a history lesson. We'll start with an old dead guy. This guy, William Herschel, a famous astronomer in the 18th century, was famous for discovering, oh, the pointer's not going to work on the screen. I just have to point like this. The planet Uranus. And he's the first person that we can name to have discovered a planet. The other 5 planets known before Uranus were known by the ancients in several different cultures. So we don't know who their initial discoverer was. So he's already famous at this point in his life. And he wants to continue doing research, and like a good scientist, he comes up with a topic. And his question is, do different colors of light have different temperatures? Is blue hotter than green, or is yellow hotter than green? I wonder. So he got himself some mercury bulb thermometers, went inside a dark room, and had some sunlight coming through a prism in the wall. Sheds it down on his workspace, moves the thermometer into the different colors of light, and writes down the temperature that he reads with the amount of light he's receiving, moves it out of the way so that it cools down, pushes it back into the light again for a different color, writes that down. Except at one point he looks down and he realizes that the thermometer is not cooling down. It's It's not here in any of the colored light, but it's not cooling down. And he moves the thermometer around and he finds there's a region that's sort of invisibly keeping that thermometer warm. And it's below the red, hence the name infrared. Now, what do you think he might have also discovered this same day? Ultraviolet. He tried, but he failed. So he immediately thought, let's move it over to this side and see if that's true there as well, and got nothing. No signal whatsoever. When a scientist goes, that's weird, that's the time I like to pay attention. They don't often say eureka. So it turns out, mystery was solved later, that the glass of the prism, which appeared to our eyes to admit all the light, only admitted a small portion. And it did not include ultraviolet, but it did include some infrared. So that's why I was able to discover it. So that later on in history leads to more discoveries of lots of kinds of light, and we find that the visible spectrum, everything that our eyes can see, is a very small portion of the spectrum. We've got all kinds of different colors of light that go beyond our eyes. So why does this matter so much for astronomy? Well, this is a constellation you should all recognize. Orion, it's up right now in about that direction, and it'll be up for several hours. I've added the blue lines to make it easy. Up here we've got Betelgeuse, and down here is Rigel, and that's Bellatrix, and Sirius is down here, and lots of other Harry Potter characters are throughout the but we think we're seeing the light coming down from the universe. Only about 20% of the normal matter of the universe emits visible light. A lot of light is emitted other than that. Here's the same image with infrared eyes. So it's rather significantly different. Take a look at Betelgeuse and Rigel, those two big stars, and how they appear here. They're significantly different. And some things that don't seem special at all, like this region here, are suddenly quite interesting in the infrared. 60% of the matter of the universe emits infrared light. So there's a tremendous amount of information to be gathered if we can study the entire spectrum of light. So there's your background on infrared. Let's go on to the next big word, observatory. Well, an observatory is just a home for a telescope. And we start off with some very primitive observatories where the most sophisticated tool is the human eye. Go to about 500 years ago, we finally get some tools to enhance the human eye. Those are telescopes. Lenses get invented. Predates photography by a couple of centuries, so the images we have from the first telescopes were hand-drawn, this one by Galileo. Move through that technology about 400 years, and we get to modern telescopes. Just look at the hill in that direction, and you can see a modern telescope, somewhat modern, it's not that new. This is the James Lick Observatory atop Mount Hamilton, and any old modern observatory can take a crystal clear image of the moon, as clear as you'd like it to be. Then we start discovering that there's other kinds of light out there. So, for example, you've probably seen radio observatories around, the ones that look like giant satellite dishes, and they can see things in all kinds of different spectrum. Often, radio observatories are in big arrays. In fact, the array that took this image up here, that is the supermassive black hole at the center of our galaxy, Sagittarius A star. And it had to be taken by an array that consisted of a small number of pixels distributed all over the surface of the Earth, and several months of data collection. Let's talk about some of the sexy observatories, the ones that we put up in space. All of these have happened in my lifetime. And just for a comparison, here's a 20th century observatory on the ground compared to the same image taken by the Hubble Space Telescope. And this picture doesn't really do it justice, but you can see that little blurs in the background are themselves entire interesting galaxies. Well, this was 30 years ago. How are we doing today? Well, we just launched a new space telescope. And here's the best image of the Southern Ring Nebula that the Hubble took, and here's the first image that Webb took of that same nebula. You can see there's a great deal more information and depth and clarity to it. So observatories have been coming along for quite some time, and they continue to do a lot of things. The key thing to remember is that the kind of light that is emitted by some object is dependent upon its temperature. Visible light is emitted by fire, things that are thousands of degrees Kelvin. If you want to get higher energy light, gamma rays, you're talking about billions of degrees, X-rays in the millions, and infrared is a bit cooler. It's down here in the hundreds of degrees. We are hundreds of degrees. Our own bodies, the surfaces around us are that temperature. When I have more time, especially when I'm presenting to much more primitive audiences, I will bring out the infrared camera and have people hold ice cubes and paint each other and show that the temperature changes the kind of light that they are emitting from their own skins. All right, let's move on to the next big word here, stratospheric. The issue is our atmosphere, which does wonderful things for the chemistry of life and our own bodies, presents some problems to observations. So here's the spectrum moving across it. Visible light is just this narrow band, and this smoggy-looking color indicates how much of that particular color of light is blocked by our atmosphere. So radio seems to have no issue whatsoever. No surprise that we have chosen to use radio for our communication devices, because the atmosphere is essentially transparent to it. Visible is the next most transparent. There's some infrared and a bit of microwave, but if you want to look at X-rays or gamma rays, you can't do it through the atmosphere. It's actually a good thing that we've got this atmosphere blocking this, because otherwise we would all be walking scabs of skin cancer. This little bit of ultraviolet that sneaks through here, that's what gives you a sunburn. Now, why did life not adapt to use radio for its vision? Well, it has to do with long wavelengths. Long wavelength of light can only resolve, that is, distinguish things that are about the same size as its wavelength. So if we had radio eyeballs, our eyeballs would be wagon wheel sized, and the smallest things that we'd be able to see would be golf ball sized. So instead, it makes sense that we have used the most resolute kind of light, which is abundantly available to us, the visible light. So we can see pinheads until we reach a certain age. Okay, but this is a picture of the Earth taken with an infrared camera from a weather satellite. And can anybody point to their house on this image? Can anybody point to their continent on this image? I think this might be the coast of West Africa, but I'm not sure. So when you look down at the Earth in infrared, all you see is the weather. You see the atmosphere. And the same is true when you look up. So if you want to look up and see that fabulous 60% of the universe that's emitting infrared light, you got a problem. All you're going to see is the Earth's atmosphere. You're going to see the weather. It doesn't matter how clear of a day it is invisible. It is cloudy in the infrared. Now, how do we solve this? With other observatories, we have different challenges. Radio, there's no challenge. You can put your observatory anywhere you want, and it will work fine. For visible, we like to go atop mountains. Let's get above the really wet, soggy clouds, and let's get above the worst of the smog and particulates. But the oxygen and nitrogen and argon that's in the atmosphere doesn't get in our way at all. For X-rays and gamma rays, we have to go to space. It's the only way to do it. And infrared is the one that's in the middle, and there is a compromise solution. So that's what we did. SOFIA is an airborne observatory. Instead of being a telescope in a building on top of a mountain, it's a telescope in the back of a 747 aircraft. It can go approximately 3 times as high as the highest land-based observatories out there, therefore getting up into the high and dry air. Turns out it's not the oxygen, it's not the nitrogen, it's not the argon, it's the water. Just the trace amounts of water vapor, that's what kills infrared observing. So we've had this operating up until, sadly, a few months ago. The last mission was held on September 29th, and it has been a joint effort of the United States and the German Space Agency, and it's been the world's largest transportable telescope, and we've spent quite a bit of time operating over 900 flights. take a look at inside of it. Well, most of it is a 747, and the really strange stuff happens back here. So we did something that Boeing never wanted to have happen to one of the airplanes. We cut a 16-foot wide hole in the side of the fuselage. That required some significant modification to the fuselage, control devices and everything. Put basically a roll-up garage door over that hole, mounted a 10-foot diameter telescope that weighs several tons in the back of the plane, and very importantly, put this pressure bulkhead here, because back here in the stratosphere, you live for about a minute. And I want to live in the front, where we fly about a 10-hour mission. And there are different people working on board the plane. Some people are operating the instrument, the camera. Some people are operating the telescope. Some people are operating the aircraft. Some people are analyzing the data as it comes off of the telescope. And there are some other people. Turns out in a 747, there's a little bit of spare room, so we can have guests on board. So if you were one of the scientists that was getting data from SOFIA, we would invite you to come fly a flight with us. If you were a VIP, you would sometimes get to fly on board. One of my favorite VIPs was Nichelle Nichols, aka Lieutenant Uhura, was on board. And if you were a teacher or a journalist, you could come on board. We flew quite a number of educators on SOFIA over its service lifetime. Let's take a look at the telescope in the back, about a 10-foot diameter telescope. This is the big primary mirror here. Light comes in, bounces off the primary, focuses off the secondary, bounces off the tertiary, moves over to here where the instrument, the camera is. And one of the biggest questions I always get is, how can you have a telescope on a plane? Don't you know they move? And if you've ever been out just with binoculars trying to look at Saturn for that pretty picture, you know that the darn thing jumps around all the time. Of course, it's you and your telescope that's doing the moving. So we have to come up with some solutions to the fact that planes move and vibrate. And there are quite a number of solutions that go into them. Anti-vibration systems to take out the high frequency buzz that's happening all the time. Active pointing systems, so we have a number of guide cameras. Also, very often in our star field, there will be a couple of stars that we know aren't moving around, and we'll track on them. We'll have devices on the back of the telescope to counteract the blowing of the wind, and a lot of other things. The simple answer is we have really good German partners that made a really good telescope that's very stable. When I've flown in missions, I can feel the turbulence of the plane. I can tell it's moving around. I look at the telescope, and I can see the telescope physically moving about this fast. And I'm sure we've lost the image. And I look at the picture that's coming off of the sort of the viewfinder of the telescope, and I look at the image, and it looks like a still photograph. It's not changing until the operator tells it to change. Really impressive tracking. Here's a non-modeled picture of it, fisheye view, so from inside up against that bulkhead, taking a look at that 10-foot diameter primary mirror that's on there. Talk a little bit about the aeronautics side of it. This group should have some interest in that. The 747 SP. It's a 747, one of the earlier models of it, and SP was for special performance. And back in the 70s, when these were being generated, the engine technology at the time couldn't make jumbo jets go as far as they wanted them to go. So if you wanted to go from Los Angeles to London, you were probably going to stop in New York and refuel. If you wanted to go from San Francisco to Sydney, you were going to stop in Honolulu or Tahiti and refuel. So there was a real demand for a plane that could make those journeys without stopping. It's quite a bit more expensive to stop in the middle. So Boeing made a small number, fewer than 40, of these 747s where they shortened the fuselage, took out about 100 seats, but extended the range of the aircraft. Today, modern engine technology makes that no longer necessary. The full-size airplanes can make those journeys, so there's not a commercial market for this. The few 747 SPs that still remain are used for things like this, scientific purposes or ships of state, such as the Air Force One of a few countries. This one was originally purchased by Pan Am Airlines. You have to have some gray in your hair to know who that is these days. operated for them as the Clipper Lindbergh, later picked up by United Airlines and then eventually purchased by NASA and redesigned rather significantly. Here's what it looks like inside. We wear flight suits, and that's mostly so that we don't drop things into the telescope or some delicate instrument or something. We fly 10-hour missions. It's not happy or comfortable to be on those 10-hour missions. It's loud. If you want to talk to people, you have headsets and radio systems to talk to people. It can be kind of cold very often. The instruments we have on board, we're often keeping cold intentionally so that people just have to tough it out. So where do we fly? We operated out of Southern California. Palmdale was our base. That's about an hour north of Los Angeles in the Antelope Valley, which is the western tip of the Mojave Desert. And we typically would take off around sunset. We'd land around dawn, fly around all night doing things. The black lines that you see in this image, these big black lines, those are dead legs. That's where we're climbing or we're descending or doing something other than science. And the blue lines, those are the science legs that we're looking at. The science legs sometimes curve in strange and unexpected ways. That's because the aircraft is moving over the surface of the Earth, which is curved, and the Earth is rotating, so the stars appear to rise and set. So if you want to watch a star in one direction, you're going to have to steer the airplane. And worth pointing out, the telescope, I'm going to be silly for a moment here. Plane points this way, the telescope points that way. So if I'm the plane and I want to point my telescope at a star, it can go up and down on its own, but to go right and left, I have to move. So I'm going to be steering the airplane around, and that was our job for a time. Both Randolph and I have been flight planners and had to plan missions like this and try to put together a jigsaw puzzle that is efficient and starts and ends at the same place so that we can take another mission the next night. We also had to worry about the weather. Not just because the weather can interfere with flights, but because the wind matters for us. Most aircraft care where they're going. And if the wind is blowing across them, they just lean into it a little bit to get to where they're going. SOFIA didn't work that way. We actually cared what direction our nose was pointed. And therefore, if the wind was going to blow, it was going to blow us off our course. So our method was instead to take a look at a weather forecast and predict what that would do to our desired path and tell the world we're planning to go there. And sometimes, unfortunately, it would blow us into places like the colors, the oranges and the reds you see over the surface. Those are places we're not allowed to fly. So more to our puzzle. Now, a big advantage of being on board an aircraft, however, is that our telescope is mobile. It can go lots of different places. So we didn't just operate out of one facility. These are several of the places that we operated out of. In addition to being able to go someplace because the conditions are good, for example, in the summertime, it gets humid and the nights get short. So we just go to winter. In the southern hemisphere, it's winter. So we'd spend a month or two every summer, usually in Christchurch, New Zealand, flying operations in winter. And there are furtive events. So how many people here have been inside a total eclipse of the sun? So not that many. I have never been in one, and it's because I've never been in the right spot of the Earth when it happened. So there are events. An eclipse is a special term. It's only the Earth, the Sun, and the Moon that line up to make a solar or a lunar eclipse. An occultation is the general term. That's sort of a target of interest, a star, and your eye. That's an occultation. And an event can happen where it becomes very interesting when something moves in front of a target you're interested in, or when the target you're interested in moves in front of a star and can get backlit by that star. So we did a number of occultations, but those shadows can be small and fleeting, and they can last seconds. I think Randolph will talk a bit more about it, but by having a transportable telescope, we were able to be there for those few seconds several times. How am I doing on time? Okay. I'm on my last slide. If we want to watch this short video of an installation of an instrument. there's a lot of them. So that was me when I was younger. I've been on this program for 14 years. The instruments are cryogenically cooled. Imagine that you're using a regular visible light camera, and you heated up your camera so that it was glowing red hot. You tried to take pictures. You would end up getting pictures of the inside of the camera because the light coming off of the glowing hot camera would be brighter than the light coming through the lens. Well, in an infrared telescope, we're looking at things that are room temperature. And room temperature objects in the room would be much, much brighter than the dim stars. So our instruments need to be cryogenically cooled. They're usually layers of vacuum, liquid nitrogen, liquid helium sandwiched around in order to keep them down to a few degrees Kelvin, a few tens of degrees for some instruments, and a few instruments were more like millikelvin and microkelvin. Okay, I'll hand it off.
Okay, yeah, thank you very much, Ken, and thanks for having us again. And now I'll talk a bit more about the science highlights that we collected with SOFIA and some of the instruments you saw just in the last video. A change of an instrument, meaning we had one telescope, but many different instruments analyzing the far infrared light and the infrared light in different ways, different wavelength ranges, which required kind of different technologies to detect them. So yeah, that video was showing installation of forecast. We're getting to some of other instruments here. I selected to start off with Hawk Plus. That was the instrument that we were latest added to our family of instruments. It's a far infrared camera with basically polarizing sunglasses, kind of polarizing filter. That allowed us to analyze the light by polarization, allowing us again to see magnetic fields. And here, of course that pointer doesn't, here you see these striations. This is the direction of the magnetic field in the Orion Nebula, a star-forming region. So these massive stars here formed in that cloud of gas and dust. But here are more forming. That's why it's kind of there. It's redder. That's the forming stars are still embedded in gas and dust, making them redder. And you see the magnetic field is pinched here. The gravity pulled in the gas and dust, getting the magnetic field together with it. Here's the Orion bar. And you see also the magnetic field changes direction here as maybe it was frozen in kind of that wall before, or now it's compressed because the radiation and winds from the stars blow this wall and form it. The study here was basically to understand how does magnetic fields and star formation interact. Is the magnetic field shaping the region, or is are the newly forming stars or the collapse before shaping it? And it's really, if you look at different regions, matter of energetics. Each region is a bit different. And for that, we kind of, a very large program was done with Hawk, looking at kind of all these galaxies, kind of studying magnetic fields on galactic scales. Again, here, images, near-infrared or optical images, underlying these patterns, indicating the magnetic fields. And basically each galaxy presents a different case. There is no easy solution. Magnetic fields in galaxies are in a certain way. There's typically, if you have a disk galaxy, in the disk following the the spiral arms, but not necessarily everywhere. And here in this galaxy M82, which has a very strong central starburst, meaning a lot of stars are forming there, a lot of energy is released, blowing out the gas and dust and ripping the magnetic fields with it. I mean, you might be wondering, why does magnetic fields and gas interact at all? That is, a lot of the gas is ionized, and so you have charged particles, and charged particles interact with magnetic fields. And even if you have only slightly ionized gas, the charged particles still interact with the gas, and then the neutral particles bump into the charged particles, and so the whole gas is coupled to the gas more or less well. So that's why studying magnetic fields is very important when you kind of look at what the gas and dust in galaxies on all the scales is doing. Moving on, what you can do when you look at stars, kind of the gas and dust between the stars, you can study astrochemistry. And you do that with spectrometers. And here we brought on GREAT, which takes radio astronomy techniques into the far infrared, allowing very high spectral resolutions, and that allows us to study chemistry, because we see the different spectral lines from different molecules. The biggest, one of the very remarkable results was SOFIA has detected helium hydride for the first time in space. And that's a very special molecule because it is thought to be the first one that formed after the Big Bang. I mean, the molecules that we observed haven't formed after the Big Bang. They have formed in this protoplanetary nebulae, NGC 7027, and the chemical models predicted that they would be there, and yes, we detected them. The same models predict that this molecule was the first that formed after the Big Bang. And so this molecule basically has started all the chemistry in our universe. But with high spectral resolution, I mean, here you see the spectrum actually, that it matches the CO spectrum from the same source that tells us, yes, it comes from that source. But what you can do with high spectral resolution is studying gas dynamics, because light also exhibits the Doppler effect. You probably know the Doppler effect, for example, from cars coming towards you, driving away from you. First, the sound is higher when it comes towards you, and then goes away. The sound is lower, so it's as the car goes past. The same happens to light. So when the gas is moving towards you, you see the light shifted to the blue. When it's moving away from you, it's shifted to the red. And here, we are going through the data cube of the carbon line, carbon emission. By the way, from the Orion Nebula, the previous image of the United Way was basically this region, so this is a much bigger map. And now, at first in the movie, in blue, you see the gas coming towards you, and then it goes slice by slice at different velocities, going to red colors, represented here again in red, where the gas is moving away, and you see a huge bubble blown into that Orion Nebula. Now, remember, this is not a 3D image of the gas, but we see image slices. But when you think there is a spherical bubble, the gas that comes towards you, which were presented here in blue and first, would kind of also make this shape. So if you assume a 3D geometry, you can infer from the gas the actual position in space. But even without doing that, you can see here the coherent velocity structures, which are probably then actually also coherent in space. For example, I just want to point out, I mentioned the Orion bar first, kind of, that is here. Let's kind of, the next, here there's the bar, and there's this streak coming along. There are also more coherent structures to be studied, the treasure trove for scientists to study the dynamics and details of how the forming stars here blow the gas and dust away from which they have formed. So, enough about that. Let's move to shorter wavelengths. Shorter wavelengths, as Ken explained, means warmer dust, warmer temperatures, and so we're looking now at warmer dust. Here, my favorite imager of that was taken with forecast. My favorite because it's of M17, Messier 17. That's a source I worked on myself, and it's just a nice image, isn't it? Anyway, again here, a massive star-forming region with massive stars have formed here, have blown a huge cavity into the gas cloud they formed from. And with forecast, looking in the mid-infrared, we can measure the peak of the light emitted, the amount of energy emitted over the wavelengths, and that exactly tells us what temperature the gas is. And so we can study basically the temperature of the dust and how it's heated from the stars, and as you go further away and further into the cloud, how it's getting colder. You can study the whole energetics of this region, how the stars destroy their parental cloud. This is a very impressive image, but more impressive is this huge panorama of our galactic center. And each lighted up, each kind of white spot, white yellow spot, is a region where massive stars heat the gas and dust in the center of the galaxy. Let me just let this go again. By the way, the full moon would be a bit larger than the TV monitor here. That's the size of it. Yeah, in the center of our galaxy, you see many star-forming regions, a lot of cold dust. By the way, the fainter part is filled in from satellite images. The brighter part SOFIA was essential to provide it. This image can't be taken in the optical, because there's gas and dust, especially dust, between us and the galactic center, and so we can't look through it. The longer the wavelength, the better we can look through the dust and then also see the heated dust. The actual center of the galaxy is here. Let me zoom in here. Come on. And now a further zoom into kind of this region where you already see there is a ellipse there. And so this is same image much earlier taken, not so deep, but you can see the brightest part, and there's a real ring there, and a very bright small mini spiral going towards. And here in the center of that ring, there's a supermassive black hole, Sagittarius A star. And forecasts allowed us to study the temperature of the dust here exactly, and so the authors were able to make a model of that heated dust ring, where the galactic center is right in the center of the black hole, but also there's a star cluster heating that dust. What is not visible is more a molecule like a disk further out, but since that's colder, forecast doesn't see it. Also, Hawke looked at this just to point out again the importance of magnetic fields. Here you see the magnetic field lines. They line up with the ring, and here it could be shown that the magnetic field is actually supporting that ring, moderating the gas flow towards the galactic center, towards the massive black hole. One of the reasons why the supermassive black hole at the center of our galaxy is relatively starved. Other galaxies gobble up much more gas and have then an active center there with huge amount of energy being released, light years long outflows coming out of the disk that forms around that center black hole. Not in our galaxy. And yeah, one reason why is that magnetic field. And now we move closer to home. SOFIA also looked at the moon with forecasts. Forecasts that didn't only take images, but also had spectroscopic capabilities. Relatively low resolution, but it was very sufficient to observe this water feature at 6.1 microns. It imaged here regions near the south pole of the moon, but definitely on the sunlit side, and detected surprisingly water there. It was thought that on the sunlit side of the moon there would be no water because it would be too hot. The sunlight would basically bake everything off, but we definitely see a water feature here, but it must be captured in glass-like minerals formed there from OH with meteorite impacts, adding a proton and then fusing it into glass beads. I mean, there's not much water. It's drier than the Sahara. But still there is water, and SOFIA was able to prove that because it has access to this mid-infrared wavelength range. spectroscopy, again, much higher spectral resolution, but again in the mid-infrared, allowed to search for methane on Mars. There had been claims of methane on Mars, but they were never consistent, really. What have here, Mars Express saw it. IRTF is a ground-based observatory in Hawaii. The Curiosity rover saw methane plumes, but it was never really consistent. AXIS, that is the mid-infrared high resolution spectrometer on SOFIA, looked again, didn't find any methane. Now you could tell me there are many lines, but yes, true. But these are lines of methane in our atmosphere, in the Earth's atmosphere, because different velocity, as Mars moves slightly different relative to us than the Earth, the lines on Mars would be slightly shifted. So what we have to do, also for all the other instruments, basically model the Earth's atmosphere very accurately, and then we see that there is no place for any methane on Mars because the measured spectrum exactly matches the Earth's model of the spectrum. So yeah, sorry, no methane there. But also these non-detections are very important scientific results. One last thing, because, well, obviously mostly SOFIA was there to observe the far infrared, or well, the whole infrared spectrum, and that's why it flew. But that makes it also movable, and then we can move it to where occultations, Ken already mentioned that happens. And here, one example, Pluto. There's an image from the New Horizon probe, which just flew past, I mean, in this image, it had just flown past Pluto, looking back towards the sun, seeing the backlit, in the backlit image, kind of that haze of in Pluto's atmosphere. Pluto has an atmosphere, which is not obvious why, and there's a haze in there. SOFIA did kind of the opposite, looked the other way, looked at Pluto just coming in front of a star, and then let me start this animation again. Measuring the brightness of that star, and when Pluto moves in front of it, it drops. You see here the star, and now you see it here also light curve. It gets dimmer as Pluto moves in front of it. Then we get a small central peak very soon. And as Pluto moves further, the star comes back. The important thing now is if Pluto had no atmosphere, this would be a sharp drop. There would be no bip in the center, and again, sharp out. But because Pluto has an atmosphere, and you can also model the haze, especially in the upper atmosphere where New Horizon wasn't that sensitive, you can model basically how that exactly is. The central flash here comes from when you're exactly aligned, telescope, Pluto and star, then the light filters all the way around. It's basically a small lens. Of course, with the center blocked, but still, you get more light. And we actually managed to put SOFIA exactly into the center of that shadow, that with kilometers and precision by a few less than a minute to actually see that central flash. So that was, well, also great feat of astrometry and flight planning. I actually had in-flight calls from the telescope, which had just observed the latest correction on where the star and where Pluto is, corrected our flight plan, and we hit it perfectly. Anyway, but we these were very occasional. We only did a handful of these occultation observations, but they were always very special operation. Yeah, with that, come to a close. The SOFIA project has ended. We did 732 observing flights, starting in 2010 and just had finished a few months ago. The observatory is now at the Pima Air and Space Museum in Tucson, Arizona, being readied for public display. Here it's getting pulled into position. But yeah, so that era came to an end. Let me summarize. SOFIA is a unique observatory platform for infrared astronomy. It carried a 2.7 meter, or 10 feet, I guess, 17-ton, metric ton, telescope inside a Boeing 747. Actually, I'm not sure if that's metric or, but anyway. heavy. It operated from 2010 to 2022 in California and New Zealand mainly, but there were also flights from Germany, Tahiti, Chile, and Florida. It served astronomers worldwide. We studied the cold universe, basically. I mentioned magnetic fields, interstellar gas and dust, astrochemistry, the Milky Way, and other galaxies, atmospheres, and minerals in our own solar system. All the data is public available. You saw here these two URLs all everywhere. This is our science site. This will soon go away within the next months because the mission has ended. The archive is here at Ursa IAPAC, and that's the URL to our mission page there. And all the data is there for a very long time at least, indefinitely, as long as that archive lives, available to everybody in the world, and the community will kind of make very good use still out from it. Yeah, thank you very much again. Now we have some time for questions, I hope. What's the time actually? I have also a 5-minute video summarizing that occultation flight. So if there's a question about that, maybe we can put that later on. But yeah, there was a question.
I'm just wondering, in all the missions you flew, did you come across anything totally unexpected or that like created new conventional wisdom?
Well, the water on the moon was definitely unexpected. I'm not sure who kind of, somebody was looking there, can we find it? So it was not a serendipitous discovery. Somebody went there looking for it, but definitely was, not expected or not clear that it would be there.
There were some operational challenges from time to time. We would occasionally find that air traffic control had different opinions about our mission from time to time. Usually they were fairly generous with us, and we'd hear our pilots chatting them up. A lot of people who are willing to work all night long as an air traffic controller, also because they're night owls, are interested in what's going on in the stars. And we'd actually train our pilots to understand what it is we're looking at. And I could listen to the pilots talking to the air traffic controllers. They're doing something with Mars tonight. And the air traffic controllers, oh, cool, let me see if I can clear some traffic out in front of you.
One other science experiment comes to mind, looking at polarization around a star. I don't recall the full science case. It was kind of one of the, as science usually is, kind of a mosaic piece in a bigger picture, but the polarization field was exactly the opposite of what they expected. So. Oh, sorry. Oh, sorry, I didn't see that.
How are you funded? It is a non-profit organization?
How are we funded? So we're jointly funded between NASA and DLR, the American and German space agencies, roughly 80-20. So 80% of the cost and 80% of the benefits, as it were distributed by the American system and 20% by Germans. But anybody in the world could apply for time on the observatory. So government funding.
So thank you for your tax dollars. Thank you very much.
I did aeroacoustics research at the big wind tunnel there at NASA, and I understand there's a very interesting noise and vibration issue with this aircraft because it may not be apparent to everybody, but it's completely open to the air. I'm guessing because you can't find a sapphire window large enough to put in there. I mean, if that
Diamond.
Considered. Diamond, right? Yes.
I'm not sure if even that would allow all the wavelengths that we want through it.
Yeah.
But I know it went through a bunch of wind tunnel tests and all that, but I think even with that, it was probably still quite loud, a lot of buffeting, and just from the air flowing over, or what was the experience?
The experience is kind of shocking. That is that when the big door opens, the pilots were very concerned that something significant would happen, like the tail would fall off. Or that the plane would start shaking and vibrating, or that it would whistle like a flute, or that a number of other bad things would happen. What ended up happening is the pilots insisted that we had to put a sensor on the door so that they knew when it was open and closed, because when they opened and closed the door, it made no difference to the performance of the aircraft. So the airfoil was worked out just right.
And if you actually look here at the model, it's kind of somewhat enough correct. There's a small bump that lifts the airflow over, and at the end of the cavity there is kind of a spoiler reaching in. Actually I have it here again in the slide, in the backup slides. You can actually see that spoiler. I think I have it. Yeah, here. You see that spoiler reaching in? That reattaches the airflow to the fuselage. And it worked perfectly as predicted from the wind tunnels here at Ames.
I'll just follow up on that. The turbulence, there are techniques to take away the turbulence, effects of turbulence. Was it done in the optical stream, software processing?
No, basically. Yeah, some. There was, well, we have here the secondary mirror, which can move because we need to make difference measurements, and therefore, yeah, I don't want to go into details, but that's also used as for image stabilization. That basically corrected the fastest modes of vibrations. And so, for the long wavelengths, I should add that at the long wavelengths, the seeing, basically what we call it in astronomy, doesn't matter much. Our beam diffraction, I mean, the resolution of the telescope goes with wavelengths over diameter, and with the longer wavelengths, you just get less and less spatial resolution, and so it's much larger than actually any turbulence or so. And so it didn't, for the long wavelengths, it didn't matter. For the shorter wavelengths, we had very sophisticated methods, including kind of here tip-tilt corrections of the mirror, stabilizing the image.
And good German engineers.
One more question. On the center of the galaxy, you showed a picture of the magnetic fields. There was a big ring, but on the northwest of it, there's a smaller ring. Could you comment on that one?
It's not my area of expertise. I don't think that I can say much about it, but let's just have a quick look at the image.
It's even further from my expertise.
Yeah, I mean, that might not be north up, and anyway, astronomical images have east and west reversed. But yeah, well, the magnetic field goes further out there as kind of this whole connects to more structure, but I can't tell you any about the details, what kind of larger the structure would there be.
Thank you for your presentation. From all the years of science and discoveries, was there anything that has, for lack of a better word, practical applications, engineering applications for us, for the world here on Earth?
Well, the astronomy, rarely, but I mean, all the technology development that went into the instruments and the telescope itself, yeah.
This is the question that every teacher of a classroom always wants us to answer. And my answer is that advancing the knowledge of mankind is always a good thing. So a few hundred years ago, Count Volta, I think, figured out with the battery, if he poked the wires into a dead frog's legs, that the leg would twitch. And everybody said, well, that's interesting, sir, but what good is it? He said, I have no idea. It's a scientific curiosity. But about 100 years later, you've got people like Edison who are using that discovery to electrify our homes, and now we can't imagine life without it. So discoveries that are made in one era become critical to life in the next. And it's up to big organizations and governments to fund these things that seem not to have an immediate practical application. But we're learning cosmology about the origins of the universe. And that's probably going to matter to us a lot more someday. Mike's coming.
I'm one of these people who believe when, not if, we settle people on the moon, permanent presence, that the water will become a water supply.
Yeah, definitely. I mean, the question is here, and I couldn't tell you the answer. I mean, there's very little water, if that's actually economical to harvest as a source. But that's kind of a very direct application. We also had observations of asteroids and their composition in the asteroid belt. So that may also be not too far from practical application where we know what these asteroids are made of.
Getting
all
water.
the astrochemistry, I guess, to understand how chemistry works out there. I mean, it's still very basic research, but understanding how chemicals form, how complex molecules form, could tell us about how life started here or elsewhere. Maybe that is not science fiction at some point anymore.
I worked on the Lunar Resource Prospector rover doing their lighting, so it's a big heartbreak when that mission got canceled. But that was supposed to actually find water in that deep crater that's always dark.
Just getting water into orbit is on the order of $1 million a kilogram. So getting it to the moon is going to be even more than that. And water is very useful for all kinds of chemistry. So discovering that it's there, even in the scantest amounts, could be very significant.
Hi, I'm just curious. Do you know, are there any other or plans for any future aircraft-based observatories?
At the moment, no.
There are not.
Yeah, I was just, maybe we actually, could you hand over the telescope?
The
Hand the
microphone.
microphone.
Get somebody here who might have a better answer than we can offer.
Yeah, may I quickly introduce our Deputy Director, Bernhard Schulz.
Hi. Well, the SOFIA was probably the last observatory of such a size in an aircraft. The problem with any more modern aircraft is they don't really house a telescope very well. Even this gigantic Airbus, it's, people looked at this and it's probably not very good. The other problem is this aircraft in particular, because we still had these very old engines, it took a lot of fuel. And it was not very economic. It cost a lot of money. Money was, in the end, the reason the mission got canceled. So we're thinking about other ways. The stratosphere is very important. It's very expensive to get into space. Everybody should remember that. So having something like a stratospheric platform is an important thing, not only for infrared, also for ultraviolet, and even for visible, because up there, the seeing, what we talked about, is much, much better. So then you can think about something lighter than air, kind of a gigantic Zeppelin, if you will, right? But in order to bring a lot of mass up into the stratosphere, so we're talking about 20 kilometers high, roughly, higher than SOFIA could ever go, you need a very big volume. So we're talking about something like 200 meters long, 50, 80 meters in diameter, something like that. But it can be done.
Well, it's not only
But it's not
interesting-
funded.
Well, it's just an idea, but I mean, it's also not only interesting for looking up, but probably also looking down telecommunications and so forth.
Well, it is very sad that it's over, but it does seem to me that one of the things that SOFIA did bring to the table was the ability to maneuver quickly and have that agility. We don't have that with satellites. We really don't have something that's going straight up. So is that something that we need to figure out how to get that done to get more of this great work accomplished?
The stratosphere being high, we didn't have to be moving to do most of what we did. We had to be mobile to do the occultations. I think we did 6 or 7 of them
Yeah.
in the
out of our couple of thousand observations. So that ability is essentially lost as well.
Yeah, I'm just going to the summary slide.
Yep.
Thank you for the presentation. So I have a question about so in your project, SOFIA, how did you guys overcome the Doppler spectra? Because, we're dealing with a bunch of, red-shifted, blue-shifted light, also the effect of the airplane speed. And, let's say the galaxy is moving away from us or approaching us. So I think that there's a huge complex Doppler effect problem. So is it by resampling the signal versus the phase modulation, or?
Well, you had to, at first, you need to very well know basically your speed and the speed of the object you're observing, depending on what spectral resolution you have. But for example, for GRADE, the radio instrument, you basically had to take all that in. Interesting, of course, only the radial velocity is important. So actually the aircraft velocity didn't make a difference because we are looking perpendicular to the direction of travel. But basically all the basically movements are known, and so you basically can correct for that. And then, well, you know what frequency you want to observe. Most often GRADE looked at the C+ line, a line of ionized carbon, 1.9 terahertz. I mean, as a radio instrument, if you're kind of working in radio frequencies, 1.9 terahertz is very high. So that was cutting edge technology. But yeah, calculating basically the velocity, the Doppler corrections was not really an issue. You just need to know, and I mean, we know exactly the orbital mechanics of the Earth, and so we have orbital velocities. We know exactly where the aircraft is, and so this is, yeah, basically pushed in some algorithm, and you don't need to kind of worry about that when you actually plan observations or so.
Sometimes the Doppler shift was actually helpful and,
yeah.
necessary. It's common, maybe we want to measure methane on a moon of Jupiter.
Well,
and
or
of
Mars,
course there's
here.
trace amounts of methane in our own atmosphere. That methane would be brighter than the signal that we're getting from the planet. And therefore we need to separate it, having a Doppler shift between the two of them. There are many times that they wanted to observe something on a moon, and given that particular month, it had to be when the moon was rushing towards us, not rushing away with us, because otherwise the Doppler shifts would be in the wrong direction and it would stack up on top of some common element in our own atmosphere.
Thank you so much for the presentation. I just wanted to ask a question that really interests me. So you've mentioned that you've discovered magnetic fields that cause nebulas to be sort of blown away from star formation. So based on that discovery, how did that revolutionize your understanding of the ways nebula behave?
Well, that's a very big area of research. How, well, stepping a small step back here, or a big step back, when we look at the gas in our galaxy and thinking of gravity, just pulling it together to form new stars, if it would be just falling by gravity, there would be much more star formation than we currently see. So the question is, what holds up, what prevents the gas from falling just under free fall? And there exactly these feedback processes come into play. Like that the stars that are forming, putting out energy by themselves in winds and radiation, which then disperse, kind of working against the gravity, dispersing the material again. And to, many regions have to be studied for that, and especially kind of, I showed the movie of the Orion Nebula. We did similarly much larger maps of many massive star-forming regions, so we can understand the energetics of these regions in a statistical sized sample. And that helps us understand that one of the feedback processes. There are many other feedback processes, how energy is basically injected again through star formation into the interstellar clouds, preventing them from collapsing. Magnetic fields is another topic. Basically, the magnetic pressure can hold up the gas. So this is a large complex that my colleagues and I are looking at to understand how stars form, how fast they form, how galaxy evolution shapes, happens with star formation is one aspect of that matter cycle, basically. The interstellar gas collapsing, forming stars, being thrown out again, and then forming again new stars. So, all I guess I want to say, that's a large area in the forefront of our studies at the moment, and magnetic fields are an important ingredient that we now more and more have access to these observations, and magnetic fields also are now added more and more into simulations of star formation. So that's where it all comes into play.
The Webb telescope was designed to look into the early universe, and I was wondering how much of that did SOFIA get to do, or was it not quite in the right, was it quite designed for that?
No, we didn't have basically the sensitivity.
Okay.
So
it was never really attempted to look at the background radiation or anything like that?
No. That was, not feasible. Also, early galaxies were just too faint it's a much smaller mirror collecting the light. We had some success looking at lensed galaxies, but that was just a niche. What is more important, that we were able to study very well these nearby galaxies, some of them with relatively low metallicity, meaning they are in some ways like galaxies in the early universe, but much closer, and so we can study them in detail, whereas even Webb just gets basically one data point, and that's a whole galaxy. We need these local analogs to understand the high redshift universe, and I think also the SOFIA data in the archive will still produce very good results that help understanding data that Webb will produce.
Another advantage of being able to land the observatory every morning is that you can change the camera. So with the different instruments, we actually have a much larger spectral range than any telescope in space.
Hello again. Did you guys ever fly through the southern anomaly that's in the southern hemisphere, or through an aurora borealis or anything really strange? Did you guys ever fly through anything like that?
So the South Atlantic anomaly it was not in an area that's in the South Atlantic Ocean off of South America. I don't think we ever flew in that neighborhood.
No.
We got to Argentina one time. So no on that. As far as Aurora, we would fly fairly close to Aurora Borealis once in a while. More often, it was Aurora Australis in the southern, because we get closer to higher latitudes. Christchurch is a sort of Portland or Seattle latitude, so we're starting several degrees closer to the pole. I never had the good fortune to be on a flight that had a really good view, despite flying more than 70 missions. It could see the aurora out there. It's gray, no, it's green, it's something.
But I was on some flights, we actually flew under aurora, but basically we are well under the altitudes where aurora happen. So it was always above us. And it didn't affect us in any way, except a little bit. Our guider cameras were optically, and so the background on the guider cameras would be increased when there was aurora, but not to the point where we couldn't track the telescope. It was just getting a bit more difficult.
Things that affected us more were thunderstorms.
Yes.
There were bad thunderstorms over Tennessee, and you were planning to fly over Tennessee. Guess what? That wasn't going to happen. So if one of us were on board, our fingers would start flying how to replan a portion of the mission to recover the lost time that we're going to experience as we detoured. The other thing is, every once in a while, something unexpected in the world of aviation would happen, and we'd get detoured around that. So somebody's having an emergency, or the military has decided to seize some airspace to do something that we don't know what it is.
Question about you mentioned the cost of flying this thing. How much money does it take to fill up a 747 for a 10-hour mission?
Actually, I don't know that number.
I think it's around $250,000. $100K.
100K, one
for a tank load. When a jumbo jet takes off, it's 1/3 of the weight is the plane, 1/3 of the weight is the passengers and cargo, and 1/3 of the weight is the fuel. So we would take off with 120,000 pounds of fuel and land with maybe 20,000 pounds.
Sounds about right.
At a few dollars a pound.
And that actually also dictated our flight plan, our flight altitude. At first, we were too heavy to go basically to the highest altitude that we wanted. So we were actually starting at 39,000 feet. And as the plane got lighter, we would climb up to 43, sometimes 45,000 feet. But that was only possible, the highest altitudes were only possible in the last hour of the flight.
Commercial flights are usually between 25 and 35,000 feet. If you've been in a modern jet on a long flight, you may have gotten up to 39. That's where we start.
All right, one last question.
Thank you again. Similar to radio astronomy, where you have a lot of different dishes to create one image, you think in the future maybe you might have smaller telescopes on drone airplanes, maybe an army of airplanes where together you create one image in the future. I don't know. What your thoughts?
Well, there are concepts to basically to put that in space. It's probably easier to fly information, or maybe why not fly separate but connected by tethers or booms or something. So that is actually in planning. And then have, with that interferometer, it's basically when you kind of combine the light from different telescopes. That's called an interferometer. Radio astronomy has advantage there. They don't need to kind of connect the light beams, but basically can record the signal in electrical signals and do the correlation later. That happened, for example, with the Event Horizon telescope. There are also plans to put a radio telescope in space that can be combined with ground-based radio telescopes to make even the Earth-sized Event Horizon telescope even larger, and then resolve even more of these galactic hole, black hole shadows. But for optical or infrared wavelengths up to far infrared wavelengths, plans are to put something like that in space.
All right, everyone, please help me thank Dr. Randolf Klein and Tim Ballard. One note two things. Number one, before you go, please clean up a little bit. Put all your trash and stuff in the appropriate bins. And if you happen to borrow a chair from that room, please put it back. And again, thank you for coming out. We're happy to put on these events for you. If you'd like to know more about us, please come and see me. Or we also have a couple other council members in the back, Thomas and Sina, if you'd like to talk to either of them as well. So thank you.
Thank you.
If you've enjoyed hearing from us, and the short answer is we're available. If you need a scientist or an engineer, we're going to be employable very soon.
Yeah, I guess we'll be here, and I just started for the next 5 minutes.